I'm Don from RF Venue. Thanks for joining me for this little webinar. We're going to talk about wireless mics and how to keep them on the air and working. We hate when they drop out, so we'd like to keep them working. So what we're going to talk about today is why wireless microphones drop out, how antennas pick up signal, how they work, and we're going to talk some tools and tips about how to improve your performance and keep yourself on the air. So there's really three things we have to think about. Once we've got our wireless mics working, we've got them wired up, we've got new batteries, we've assigned them clear channels, everything's on the air, we're doing our sound check, and we're good to go. So what often pops up is in the middle of a show, the mics start dropping out. And we want to know why that happened and what we can do to avoid it, because obviously we don't want that to happen. So here are the three principal reasons that wireless mics, once they're working, tend to drop out. We've either gone out of range, we have too much multipath reflections for the receivers to deal with, or we have polarization issues with the antenna. So we're going to run through those. Range is probably the easiest one to understand. You simply have to get the signal from your transmitter to your receiver. So what's the range of that? How far can I get from my antennas? And the answer to that is how far you can get with a usable signal, because you can get thousands of miles, but the signal is so tiny, the receiver doesn't have the ability to distinguish it from the noise floor and dig it out and put it up on the air. So what we're really looking to understand is how far we can safely be away. If we look at typical wireless microphone specs, we're going to see that they pretty much all call out 300 feet, and then they warn you that's all in relation to local interference. Local interference is really the key to all this. In other words, what's the noise floor at your venue? So if we look at a scan online, this one's particularly horrible. There's probably 125 little wireless microphone spikes here that we're seeing. And the question is, in this environment with that noise floor, and the noise floor being the sort of solid green across the bottom, how many of these microphones are going to work and how many of them are going to drop in and out as the show goes on? What is a usable signal? Really what we're trying to do is maintain a signal that's at least 20 dB stronger than the noise floor. So if the noise floor is represented by that red line on the bottom, it's somewhat arbitrary because it's different at every frequency. What we're trying to do is make sure that the signal that gets to the receiver is at least 20 dB hotter than that noise floor. Oftentimes it's much more, 40 dB hotter. But if you're getting close to 20, your toes are pretty close to the edge of the cliff and you may have problems depending on what happens on that stage. So what we're trying to do is achieve a signal that is at least 20 dB hotter than the noise floor. So if we go back and look at this, what we're going to see is I've set the noise floor, I've called it where that red line is, put a 20 dB window. So all those little spikes that are above that green line are going to likely stay on the air and not be problematic. You can see there's one or two of them that are just a hair over that green line. So, depending what your risk tolerance is, I'd be looking at doing something about those, moving them to a different frequency or something else. The lines that are nice and healthy above that green line, those mics are probably going to work all day long. And the 50 or say 70 that are below that green line, they might be on a little bit of the time, but they're not going to remain on. Those are going to drop out constantly. Again, what we're trying to do is create that signal to noise ratio, or with wireless microphones, we call it carrier to noise ratio. Because what we're dealing with at the bottom ultimately is interference. And this changes from venue to venue, from where you are. You move a quarter of a mile down the street, it's all new again. Maybe you move 300 yards, 100 yards. It's different every place. So we have to know what the noise floor is at the venue we're at, And then we got to get that signal 20 dB above that noise floor. So what's causing that noise floor? Well, here's a list of the top interferers. Of course, TV stations are at the top. 500 kilowatt radio transmitters on a frequency very near to where you're going to operate, obviously can cause problems for 150 miles. So we need to know where the TV stations are. If anybody else turns on another wireless mic in the venue or close by, that could be a problem. The new 71 band cell phone service in the States, T-Mobile has that, the pink lightning bolts. I'm not sure what all the carriers are in Canada, but most of everybody in Canada is pretty close to the US border, so you're probably being hit by this anyway. Other things that can be in your venue that can be problematic, security radios are FM, and they're a little lower than your wireless mics, but they're very close. LED lighting is a new interferer. So if you have utility lighting, just the plain lights in the building, or you have LED stage lighting, you have uplights, you have power cans, all those kind of things. If they're LED bulbs, the power supplies may not be shielded well enough, and they may be scattering a lot of interference at the low end of your band. Likewise, video walls, video projectors, large screen, TVs, all those things tend to generate RF. Basically, anything in your venue that has a motor, anything that has a computer chip is spouting out some kind of RF energy, and any RF energy that's in the band we want to operate in is competition. So all of these things together are creating that lower green boundary, the noise floor. In a very good location, that may be close to minus 100 dB. In typical locations, it's usually at about minus 90, maybe minus 80. Those are usually pretty easy to deal with. If you have a difficult location, you're in a casino, other things. If you're higher in elevation, it's harder to do wireless on the 6th floor than on the ground floor, because higher up in the air, there's more garbage. So any of these things, and including natural sources from outer space, the sun, the stars, alien invaders from Mars, all these things are creating RF interference that is adding to that accumulative effect of the noise floor. So to improve our range, we need to improve that noise floor, because again, if we're standing out in a wheat field in the middle of Saskatchewan, that wireless microphone may do a quarter of a mile. You take that same gear, don't change anything, but you move it to downtown Manhattan or downtown Los Angeles or downtown any big metro area, and there's so much other interference going on that quarter of a mile might be reduced to 30 feet, because it's just trying to compete with too much other rogue signal in the area. So what we want to do is improve our carrier to noise ratio. So the first and easiest thing we can do is make sure that we have proper line of sight. In other words, your transmitter should be able to, if you were eyeballing through it like a gun sight, you ought to be able to see the antenna with a straight line with no interference. No walls, no metal racks, and obviously not through the middle of people. So as we show here, we got the receiver down on the floor in red. You need to raise those antennas. I don't care where the receiver is, but you need to raise the antennas above head height. So if you've got your antennas on a desk at a booth in the back of the hall, and your audience is seated, when they stand up to yell, applaud, cheer, whatever they stand up for, and they're blocking that antenna, you may go off the air while they're standing up. Radio does not like to go through bags of salty water. So you need to make sure that the antennas are at least just above their head height. I would caution, you can place antennas too high. 20 feet in the air is too high for antennas generally without some other things being taken care of. So the ideal spot usually is to be about 8 or 10 feet above the floor. So here's another big problem that we run into. Uh, we call these antenna farms, where you put a whole bunch of receivers together and all the antennas are in very close proximity to each other. So when you have an antenna, it's pulling a certain amount of energy out of the air. If it pulls it out of the air, it's not available for the next antenna, right? Because it's been soaked up by the first one. Also, antennas, they introduce interference. I'll show you this in just a second. So they interfere with each other in proximity. You can move them farther apart. If you move them more than 3 feet apart, that's probably good. But you know, if you've got a lot of mic channels, that's going to make for an awfully long desk. You're going to have to spread these things out over. Also, when you put antennas together, you create patterns, much in the way that when you stack speakers, you can create a line array. Well, the same thing happens with antennas. So when we stack them together, we do it on purpose to create patterns, but we know exactly what frequencies, and we're dealing with some very specialized lengths and some isolators and those kind of things to get them just where we want them to be, so we know where they're going. When you stack them like they are in these pictures, who knows what direction you're actually picking up from, what direction you're not picking up from. It's very difficult. And the fourth thing here is polarization. And that really relates to the antenna's ability to pick up a signal that you're throwing at it. We'll dive a little deeper to that in a minute. Here's something that most people don't think about, but when your transmitter, your wireless mic over here on the left, sends out the radio waves through the air, they're absorbed by your antenna, they go down into your receiver. When they hit that first stage, they're not all accepted. Some of them get bounced back out. Usually at a ratio about like this. About 90% actually goes into the receiver, about 10% bounces back out. You may be aware of this factor when power amps go into loudspeakers, the same thing. There's a thing produced called back EMF, where all the power doesn't go into the speaker. Some of it's reflected back and it's pushing against your power amp. Same thing happens here. But of course, if I've got, if I've got a wall of antennas right next to each other, then, each of those antennas, in addition to sucking in signal, is transmitting it back out, and they're right on top of each other. So it's very easy for even those low-powered 10% that's coming back out to imprint itself right on the antenna that's right next door. So we want to avoid these. The way that we avoid this is we have an antenna distribution system. So we make a system, Distro 4 is the most simple system. You plug a pair of antennas, or preferably our diversity fin, into that, and then you can directly connect 4 receivers to that. Now you've only got one set of antennas, and you've got 4 receivers. You can combine Distro 4s, and you can create up to 25 channels with that one pair of receivers. Or you could use our Distro 9s, and you could connect up to 81 receivers to one pair of antennas. So what we want to get rid of is wireless mic antennas, and we also want to get rid of in-ear monitor antennas, which we're seeing here on the right. Very bad to have your in-ear transmitters right next to your wireless mic receivers. You're screaming at them. You're just going to blow those up. So that would be a big problem. Another thing you want to do is keep your antennas away from boundaries, particularly metal boundaries. You don't want to set up your DJ gear next to a metal roll-up door. Metal just has way too many reflections, and just like trying to run a microphone in a basketball gym, there's way too much echo. So when we put antennas next to boundaries, we get a lot of reflections into the antennas, and we're sending tons of echoes basically into the receiver, which it has to deal with, and it'll handle it to a point, and then there's a point where it won't handle it. So basically any wall we want to keep away from. A good distance is 6 feet when possible. There are some exceptions, but when you have the choice to be away from a wall, be away from a wall. Obviously moving the transmitter closer to the receiver's antenna, not the receiver, but the receiver's antenna. So we can put the receiving antennas up on the stage, we can run coax to the receivers, but we get the distance from the transmitter to the receiver as close as we can. Actually, there's a limit. You got to be at least 6 feet away from the antenna, but something reasonably close. So this is just basic inverse square law, just like it is with speakers. You have your loudspeaker. The farther you get away from it, the quieter it becomes because it loses power going through the air. And so do your radio transmitters. So if you can cut the distance in half, you will raise the signal by 6 dB. The noise floor will be relatively the same because it's basically the same all over the venue. So the noise floor will have only minute changes to it. But if we can move the antennas up on the stage instead of back at the sound booth, if it's a difficult situation where you really need to increase that carrier to noise ratio, that's one way to do it. So you can see, going from 50 feet to 25, I get a 6 dB stronger signal. Going from 100 feet to 25 feet, I get 12 dB more. So I've improved my carrier to noise ratio by 12 dB. So if we're close, our toes are hanging over the edge, we're right around 20, obviously adding 12 dB or 6 dB more on top of that gets us up to, 26 or 32, and we won't have any problems with that. So you don't always have to do this, but it's a good practice when you can to be reasonably close as you can. So here's a new one. In the States, T-Mobile has this 71 band service. I'm not sure which provider does it in Canada. Obviously, if you're close to the border, you're getting hit by T-Mobile. I don't know who does it at Rogers. I don't know who does it up where you guys are, but it's the same thing. So what's happening here, and this is the reason the 600 band got sold off. Turns out that if you do cell phone service in the 600 megahertz, that a single cell phone tower will cover approximately 200 square miles instead of a couple square miles. So obviously, if you're in the cell phone biz, that saves you a lot of money. You don't need nearly as many towers, all the maintenance, all the stuff that goes with it. So the cell phone providers in the States, T-Mobile paid $8 billion for the license to be there, and they're very close to where you're operating. So again, every radio that's on, every transmitter that's on interferes with every other transmitter. And even though they're out of band, they're not very far out of band. And so having a lot of this cell phone service going on in or near a venue you are creates additional noise in that noise floor down to about 550 megahertz. So it's creating junk. And this is going to get worse, and it's going to get worse fairly soon. So this band 71 is a 5G service, but frankly, as of today, almost nobody has a 5G phone. That'll change when Apple releases iPhone 12. That'll be a 5G device. So anybody in your audience that has a T-Mobile cell phone, a 5G phone, an iPhone 12, there's other brands, of course, all of a sudden they are creating a ton of competition to your signal in terms of a raised noise floor. So we have a solution for this, and that is our bandpass filters. So bandpass filters, you're probably aware of bandpass filters in electronic speaker crossovers. The bandpasses separate. You can see there's a couple of areas where the signal is transmitted. You look at the graph there, and then it's not received, I should have said, and it's not received on either side of that. Much like you've got lows, mids, and highs. In this case, we're looking basically at the mids. So we look at the mid crossover point. We're excluding the tweeter from getting down into the mids or the mids getting up into the tweeter. We're looking about keeping the lows out of your mids and distorting them or blowing them up or whatever. So putting these bandpass filters on eliminates a lot of out-of-band interference. Can't do anything right where you are. We need that space. But by eliminating competition from just above you and just below you, you can create a much lower noise floor. So let me show you how this works. So basically, you pick the appropriate band. We make 3 or 4 of these. You pick the right frequencies that your mics are going to operate inside those numbers. And here's showing you how it lops off the top. In this case, lopping off, pretty well obliterating T-Mobile. You see that just gets chopped off. So that energy never reaches your wireless microphone antennas, and then it doesn't go into your distro. It doesn't get shoved into your receivers. Your receivers can handle some of it, but it gets to be a point where they can't handle it anymore. So by just eliminating it from getting there in the first place, makes the job of the receiver much easier. But you can see we've also dropped the noise floor. The top, without the bandpass filters, you can see how high up that yellow line is from the bottom, and you see we've dropped it down quite a bit with the bandpass filters on. So maybe here, this is an easier way to see it. On the left is without the bandpass filters, on the right's with the bandpass filters. And you can see I've carried over that noise floor. And in this particular case, it managed to drop the noise floor about 12 dB. The same as moving your 100 foot away from the antenna to 25 feet. So if you could do both of those, that would be a 24 dB improvement in this case. That's all you need, right? So that's not always 12. It's somewhere in the real world between 6 and 12, maybe 15. Just depends where you are and what interference you're seeing. These are a simple way to greatly enhance the reliability of your system, right? We got it up, we got it running. We're just praying we get through the show without any dropouts. You drop a couple of these babies in, very simple, no power required, nothing to tune or adjust. They just cut so much interference from progressing into your system that you're likely to just stay on the air and not have any problems. And this, again, this is going to get worse as lots of people begin to buy 5G phones over the next months and years. That interference from the 71 band cell phone is going to become much, much more prominent. So what works for you today may not work in 3 months, 6 months, a year. I don't know. It depends where you are. But it's coming fast. And this is also, on the bottom end, this is also lopping off some interference. It doesn't do as good a job because there's more of it, but LED lighting, it'll cut a lot of LED lighting interference. It'll cut out security radios. It helps a lot, not quite as much as it does on the top here, but again, improvement on the bottom end. So you're getting help on both sides of the band. So to improve our range, what we want to do is make sure that we've got line of sight. We're going to make sure that we're using the smallest number of antennas that we can. And that means antenna distros, that means in-ear monitor combiners, which are basically the same thing. Let's get it down to just one pair of receiving antennas and a single transmitting antenna for IEMs. We want to avoid being around metal objects. You ever have a chance to, walk outside and walk by a big aluminum roll-up door, you'll see that your mic level drops, your RF level for your mic drops significantly. So avoid metal stage pieces, avoid lighting trusses, don't hang your antennas off lighting trusses, stay away from metal. Distance, we want to be as reasonably close between transmitter and receiver as is possible. Not always possible, but there is a limiting factor there. So let's, if we can be closer, we'd rather be closer than being far. And we want to stay away from other devices that radiate RF interference, electromagnetic interference. Electromagnetic is, of course, what radio waves are. Back in those pictures we were showing of the antenna farms, you've got other digital gear in that rack. Anything digital is spitting out RF garbage. Count on it. Any computer chip is doing it. You don't want to mount antennas in a rack that has any other digital processing in it. So these are some things we can do to improve our range. The next thing on the list is multipath. And multipath is just simply reflections. So I'm going to go back to miking in a basketball gym. Very difficult. It's very difficult. The speakers are bouncing off of everything, and that's what happens with radio. So this is pretty easy to understand. The direct signal will have the least impact. Whenever you receive two nearly identical signals, but they're a little bit out of time, they're also out of phase. And when you get very much out of phase, you start getting cancellation. So when they're completely at opposite polarity, when they're 180 degrees out of phase, you get 0, provided the signals are identical in strength and in content. Anything more than about 120 degrees, you start rapidly losing signal completely. So there's not much you can do to avoid reflective surfaces. I'm going to tell you, it's really hard to do wireless, in the boys' gym with all the lockers around, or out maybe in an industrial warehouse that's full of pallet shelves of, metal racks and that kind of thing. That's going to be a tougher environment. We have a little help for that. I'll get into that later with an antenna solution that will help minimize this. But this is just something you need to be aware of. If you're at a location that has a lot of metal reflecting surfaces, metal trusses, and they don't have to be exposed. Remember, they can be behind the wall. Any place there's metal, you're getting reflections. So reflections are not our friend. But here's one that most people aren't aware of. Another big reason for dropouts to an otherwise running system is called polarization crossfade. And what that means is the antenna has an ability to pick up the signal coming at it, and that ability changes as the angle of that antenna changes. So let me show you how this works. So if we're looking, we got a wireless microphone over here on the left. We're holding this straight up and down from 12 o'clock to 6 o'clock. On the right, I have basically, I have two antennas which are representing the diversity antennas of my receiver. In this case, we've got them hooked up to meters so we can measure the relative signal strength. But in normal use, that would be your radio receiver, one box, but there's two receivers in it. You only need, and you only get one at a time. Having a signal in two isn't any different than having a signal in one, because the antenna will switch between one or the other. So you only need one to work. You only get one to work. Okay, so when the antenna in your transmitter is straight up and down from 12 o'clock to 6 o'clock, and your antennas on your receiver are up and down 12 o'clock to 6 o'clock, you get perfect transfer. You get the maximum capability that your antenna is capable of receiving. And of course, different antennas are different, but they're at their max sensitivity when you do that. But we know this microphone is going to move. That's why it's wireless. That's why it's not locked down on a stand. If I simply turn that transmitter to a 45-degree angle and talk at it like this, I'm going to lose half power at each of those antennas. The antenna no longer can soak up as much power as it could when it was coming straight at it. Now, half power sounds like a huge loss, but remember, we look at things logarithmically, so we're going to use dB. It's a 3 dB loss. Frankly, if you're within 3 dB of falling off the edge of a cliff, it's a pretty scary day anyway. 3 dB should keep you on the air all day long. I wouldn't worry about this much. Your radio is going to pick one of the two based on some other things as well, besides signal strength. So you're good to go with this. But here's what happens. Should you turn that microphone straight out horizontal, so it's going from 9 o'clock to 3 o'clock, your antenna loses 21 dB of reception ability. In other words, your radio is now less than 1/100th. It's actually 1/128th of the power that it would have been when it was straight up and down. So obviously, microphones are moving. That's why we've got wireless. We want them to move. So this is constantly moving up and down, moving up and down. If you drop 21 dB off both receivers at the same time, you are off the air. That would be very difficult to maintain connectivity at this point. So when this happens, if your two antennas are straight up and down, now we usually twist those antennas, but if you're an installer, you go twist them, you come back, somebody will have helped you out and straightened those babies out for you. It's just what happens. Every time I go to a trade show, I look at the large manufacturers and they've all got their antennas straight up and down. They don't even understand how they work, but at least the sales departments don't. Anyway, you don't want to do this. So we have a solution for that. And this is our DFIN, diversity fin antenna. This is two antennas. This is A and B in one package. You connect two coax tables to this, but you only physically have one unit. So you can see you have one antenna that is vertical and one antenna that is horizontal. And there's some other tricks to this we'll talk about. But look, we're just talking about polarization right now. So let's see how this one works. Well, when we go back to the first, 12 o'clock to 6 o'clock transmitter, you can see I've got full power reception, actually no loss. We're looking at loss here in the meters. So I'm zero in one side and I'm horrible in the other side. But remember, your radio is only ever going to look at one side and discard the other side. So this is a perfect solution. This is really good. When I turn that mic 45 degrees, I'm going to get a 3 dB loss in both of the antennas of this guy. And again, that's not really a problem. That should be good to go all day long. However, with this antenna, 3 dB is the absolute worst you can ever be, because as you begin to move, you're going to get stronger in one and weaker in the other, as shown here. Now I've gone the complete polar opposite. Now I'm perfect in one antenna and I'm dead in the other antenna. But again, I only need one antenna. I only want one antenna. I can only see one antenna. This is perfect. So, we're going to go between 0 and -3. -3 is the absolute worst this antenna can ever get. This is going to solve that polarization issue down to -3. So you're 99 point something big % of never having a polarization issue, crossfade polarization take you off the air. And this happens. And that's just the straight signals. Obviously, there's a lot of other stuff. Well, let me show you. So here we are. I've got a transmitter. We're turning it sideways. You can see on the A and the B on the receiver. We're switching just the way you would expect it to be, because we're very close to this antenna. We're not being affected very much by the outside world. But of course, we live in the outside world. So when we take this and put it in a little different environment, here we are walking around our shop. You can see kind of a fuzzy out of focus DFIN right in the front of the picture. Alex is walking around the shop with that microphone, holding it as best he can straight up and down. So it shouldn't be shifting polarity. But as you can see, by looking at the RF meter on the receiver, you can see the A and the B lights going back and forth. And the reason that is because all the bounce is off metal. Studs in the wall, lights on the ceiling, there's some metal frames, there's some legs to our desks. All these things are reflecting back at different polarities. And so that's something that we don't want to happen. The other thing I should point out, we talked a little earlier about multipath. If you were to do this with a pair of shark fin or even just whip antennas, you would have seen those A and B transfers going back and forth, I don't know, 100 times more than they were. In this diversity fin, what we've done is we have, let's go here. What we've done is there's a stronger antenna and a weaker antenna. And that's done on purpose to help mitigate multipath problems. In other words, let's don't switch to that other antenna just because uh, it's stronger. Let's make it so it can't be stronger. Let's make it so to switch to that other antenna, we really need a polarizing uh, reason to do it, not just a signal strength. Now, usually with diversity systems, uh, they're looking at signal strength. If you're using conventional antennas, if you're using whips or paddles or whatever, they're simply looking at the strongest signal. And the diversity will switch to the strongest signal. But the strongest signal isn't always the best quality signal. So with the diversity fin and our method of doing this, we're switching back and forth between A and B based on signal quality, not signal strength. So, 8 times out of 10, signal strength does equal signal quality, but not always. And so you'll get a little more higher quality signal by using this antenna. You'll get the highest quality signal you can get by using this antenna as compared to any other conventional antennas. So we just build that in. You don't have to do anything about it. It's plug and play. You just plug it in and go. So let's go back over this a little bit. Again, we've got our mics all set up. Everything's tuned. We certainly remembered to put new batteries in it so we don't run out in the middle of the show. Can't help stupid, but we can help. We can help some other invisible things here. So we want to be concerned with our range. When we set up, we'd like our transmitters to be reasonably close to our antennas. We want to use antenna distros. Frankly, I would not attempt to do 4 wireless mics without an antenna distro system. You're just heading for headaches. So we want to use those, and we want to avoid outside interference. Again, the bandpass filters, I'm telling you, these are frankly miracle workers. If you're close to the edge, these things are just going to lock you back in. Maybe you're not that close to the edge today, but it's coming very soon. So we want to avoid interference. Certainly, we don't want to put our security radios anywhere near our antennas, or we don't want to put our Wi-Fi access point next to our antennas, even though it's out of band. Usually Wi-Fi is typically not going to bother you anymore these days. I don't worry about it very much unless I've got an access point right next to my antenna, right? So range is range, right? Range is simple. If we're sitting in my living room and we're talking to each other, we've got our normal speaking voices, right? However, and we're socially distanced these days, right? So we're a few feet apart. But if I get up and I put my mouth 1/4 of an inch away from your ear and talk at the same level I was talking to you from the other side of the room, you would say I was screaming at you. Well, actually, the energy from my mouth didn't change, but the proximity changed. And because I got so close to you, yeah, I'm screaming at you. So avoid putting other things that might have anything to do with RF near your receiving antennas. Multipath and polarization, well, there's the answer right there. All in one, plug and play, easy to use, don't adjust nothing, just plug it in. Like I said, 2 cables, 2 coax cables, use good coax, but that goes without saying, whatever you're doing. And plug those into the A and B side of your receiver or the A and B side of your distro. You will help with multipath, and you will better than 99% eliminate polarization crossfade simply by using this antenna. If you would like some more information about any of the topics we talked about today, or actually hundreds of other little topics, we have our blog. And if you go to our webpage, rfvenue.com, you can drop down all the way to the bottom of the page, way down at the bottom. There's a list. I'm only showing the top of it here. There's actually hundreds of articles. And you can thumb through those articles. They are slightly technical. Actually, we're in the tech biz, but there's not a lot of math involved with these. They're pretty simple. They're mostly rules of thumb. And if you understand all the rules of thumb and you do the best practices as best you can, you're probably going to have a pretty good time with your wireless. You're not going to have that many problems. However, if you don't understand what it is exactly you're doing and you make rookie mistakes because you don't know any better, why, that could take you off the air. So I invite you to take a look at our blog at the bottom of the page. And also, here is my contact information. You can send me an email. I'm don@rfvenue.com, or there is my direct phone number. I'm in California, Pacific time. Please don't call me at 4 in the morning, but you are welcome to call me with questions. You are welcome to call me if you need to know how to hook up this brand of microphone with this brand of antenna, with this brand of distro, with this brand of cable. I'll help you sort that all out, because you have a system that has to work together, and there's many manufacturers going to be parts of your system. So you are welcome to call me, or you're welcome to call any of the tech help there at Ericsson. I thank you for sharing this time, and I hope that helps you and eliminates some of your dropout problems and some of your sweating that you're going to have dropout problems. So we know how that goes. So anyway, thanks again for watching, and we'll see you down on the blog. Bye-bye.